You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Peter Schroedl for a fascinating discussion of one of Earth's final frontiers. Peter Schroedl is a PhD student with the Marlowe Lab at Boston University. He investigates the macrocosm to the macrocosm with a tenacious appetite for science. His current work combines geochemical and microbiological principles to characterize deep sea chimneys. He has a BS in Earth Sciences from the University of Minnesota Twin Cities.
Peter Schroedl, welcome to the program.
Hi, John. Thank you for having me. It's a pleasure to be here.
Now, Peter, you have discovered something unexpected and cool that has wide astrobiological implications. And it is the idea of dark oxygen production deep in the ocean that is not photosynthesis. It's a separate way that perhaps something involving life is also producing oxygen. And you've done some work in other areas of that. But we are talking about something that honestly terrifies me, and that's the ocean. The ocean, I'm usually talking about space and space science, but the ocean is unfinished territory for science because we know so little. One area, and that's where we're going right now, is the Clarion-Clipperton Zone, the CCZ abyssal. Tell us about this place. What's it like?
Yeah, so the CCZ it's a fascinating part of our ocean. Now, the area that we're talking about is roughly 4,000 meters deep. So it's really deep, right? There's no sunlight. It's what we would call aphotic. So it really does present some unique challenges for these microbes. It's also what we would call oligotrophic, which just means that there's not much carbon or other nutrients around for these microbes and other organisms to use as part of their metabolisms. So for perspective, I think it's around 300 milligrams of carbon per year per meter squared. So that's basically, if you had like half of a sugar cube or roughly a sugar cube of carbon for the entire year, that's how much food you would be getting. So that really presents a lot of challenges for the organisms that live there. And one of the things that is also happening is you have nearby seamounts that are sort of producing reduced metals. And through a variety of different processes that we refer to as hydrogenetic and diagenetic processes, you have the formation of nodules. And these nodules are key for the organisms that live there. The vast majority of them are either directly or indirectly linked to the nodules. And it is a really special place. This is going to sound a little funny, but I've never seen water that blue while I was out there. It's crystal clear.
Now, what depth are we talking about with this area?
So it's about 4,000 meters deep. So that's about 12,000 feet. And I think planes fly at 20 or 30,000 feet. Just for some perspective there.
So we're talking like Titanic deep, the wreck of the Titanic. That
yes.
Very, very high pressures, I would assume.
Indeed.
What kind of a submersible do you have to use to send stuff down that far?
Wow.
Just to study it. I mean, I would imagine you'd need a pressure vessel if you're going to go down there.
Yeah.
And of course that's important because of that recent implosion at the Titanic.
Yeah.
But what do you use to just generally study this environment? What is it? It's just completely remote.
So there aren't very many submarines that can actually go that deep. I think the Alvin has recently been retrofitted, and I think it could reach that depth. I think there's a few other governments that have submarines that can go that deep. Now, on the cruise I was on, we were using three main instruments. One was the deep sea lander that Dr. Sweetman uses at locations all around the planet. And then the other two were things called a multi-core and a box core. And these are more or less instruments that we would use to try to scoop up both the nodules, sediment below that, and then some of the water that's directly above it. And then that's transported using a winch. So it's basically like a giant pulley to bring it all the way back up to the surface. And so you can imagine if we're 4,000 meters deep, it does take quite a bit of time to do that. We're talking a few hours just get down and back up again.
Now, the source of that carbon that you mentioned, that sparse amount of carbon that life down there gets, is that mostly just the remains of flotsam from above that's falling down? I mean, is it sedimentary is what I'm asking?
Yeah, right. So you're exactly right. As you look across at the horizons, there's no land, there's no islands, there's nothing like that. So you lose a lot of that transport from rivers or other sort of, if you have a storm and maybe you get some dirt that washes into the sea, right? So there's none of that. And on top of that, because the nutrient content in the surface is also pretty low, that tends to mean that you have a lot of sort of recycling of these nutrients just in the surface zone itself, just because they're so valuable. And that creates a really limited supply down to the deep. And then again, you have 4,000 meters just to get down to the seafloor. And so that creates basically a lot of time for organisms that are in the water column to scavenge those particles as they're sinking. Great question.
Now, where is the Clarion-Clipperton Zone for reference in the Pacific? And is it, and how remote is it? Is it like close to Point Nemo, which I think is the furthest you can get from any human, where is it at? Yeah,
so Point Nemo is in the South Pacific, I think kind of halfway in between like Australia and South America. I think it's a little closer to South America. Now, the Clarion-Clipperton Zone is near the equator, and it encompasses an extremely broad region. So it's about the width of the United States, and it stretches kind of between these two fracture zones. And it's a little bit south of Hawaii. So I think it's roughly like 4 degrees to 15 degrees north. And it's got a really long latitude that it spans as well. So for example, on the cruise I was on, we went due south from San Diego for about 4 days before we reached the field site.
Distant. Mm-hmm. So let me ask you this. When you went down there, you weren't expecting what you found. And you would expect that area of the ocean to be relatively anoxic. It turns out not quite. Tell us about that discovery.
Yeah, so the concept behind these deep sea landers, and this has been demonstrated many times before, both with the lander that Andrew was using, but also other landers as well, is that as seafloor organisms conduct respiration, so right, if you take a deep breath with me, we're taking in oxygen and we're breathing out CO2. Now, unfortunately, CO2 will turn into things like carbonic acid, so that's like H2CO3, HCO3, and CO3 2- in the water. And so it's a lot easier to measure one chemical species than it is to measure those three. And so you'll use stoichiometry to estimate the amount of, basically, right, if your oxygen goes down, then your CO2 is probably going up. And so that is the sort of the prevailing wisdom that has dominated these deep sea incubations and lander studies. And in this case, we didn't necessarily see that. So we saw dark oxygen production from these pretty substantial increases. But what was kind of interesting too is it seems like these two processes are likely in play together. So you can have production and consumption occurring at probably the same time. And this is an aspect that this was an assumption of these earlier studies that may actually indicate a little bit of perhaps reevaluation. So if this mechanism is producing oxygen, that could sort of, underestimate the amount of respiration that is occurring at the seafloor. Does that make sense?
Yes, it does. Now, let me ask you this. This involves very deeply polymetallic nodules. Now, we've known about these for a long time. This was the cover story back in the 1970s when the United States wanted to recover a Soviet submarine with a giant ship they purposely built for it, the Glomar Explorer. Their cover story was that they were looking at these nodules for mining. And here we are again, looking at them for oxygen production. So what is the mechanism that you can identify regarding these nodules that's producing this?
Yeah, so there's some competing hypotheses right now. The one I believe we referred to most directly in the paper was basically the nodules have been referred to as little, essentially, geobatteries. And it turns out that they actually behave a little bit like batteries too. So we have measured the voltages on those, and that's one hypothesis for what could be producing this. But I actually think it could be more of the sum of several processes. So we also measured the amount of uranium and other radioactive elements there, and this has been measured by many other studies as well. And we know that the amount of radioactivity down there is quite high. Now, over the time frame of the incubation, right, so that's only about 2 days, there shouldn't be enough radioactivity to occur to account for that much oxygen. There's also a potential for a biogenic component. So our own research showed that somewhere between 20 to 40% of the community could be closely related to a microbe that, in culture at least, produces oxygen as a waste product. There's also other things. So, for example, you can have oxygen infiltration from seamounts that ultimately sort of seeps its way down there. But we were able to at least not completely eliminate, but certainly point to the likely mechanisms that could be occurring. And this is a non-exhaustive list. So there's all sorts of other things that I'm not discussing now that can also produce oxygen in the dark. But we think, or at least I'm of the opinion, that it's probably the sum of several of these processes, and it might not be of the same proportion. So what I'm saying there is, I think in the paper we explicitly referred to, we weren't able to produce as much oxygen as the measured signal from the radiolysis or from geochemical decomposition, but we were able to account for some of it. So I think it is perhaps a little bit misleading to say that it's just one mechanism when we haven't quite narrowed it down what in fact is producing it if we've only observed it. So I think there's a little bit more study that needs to happen before we can really nail down the exact mechanism that's producing this.
Now, a biogenic component, you say, and that's the involvement of life with the formation of the nodules. What kind of life would that be? Is it anaerobic? I mean, is it really, really, really old, primitive life that can do this, or is it something a little bit more complicated?
Yeah, so, okay, anytime I have archaea in a sample, I start to get excited. And in part, that's because we've been able to benefit a lot from them. So, for example, PCR tests were enabled by a discovery of a thermophilic archaea from, I think it was a Yellowstone hot spring. And even CRISPR was identified, so that's a gene editing technique, was identified in, I believe it's a halophilic archaea. And so the microbes are the world's premier geochemists. They can transform things, they help us with bioremediation, reducing the effects of radioactive waste, things like that. So they really do have a lot of applications that may be very helpful for us. And so down here, the ecosystem is dominated by nodules and deep sea mud. And the sediment and the nodules do have different community compositions, but some of what we suspect are the key players are present in both. It's also interesting to note that the CCZ is oxic to a very deep level compared to many parts of the ocean seafloor. So some studies have measured it as far as, I think it was 4.5 meters deep, and you still have oxygen. And this is important because in many parts of the seafloor, it goes anoxic in as little as 10 centimeters. So this is that's a very different profile, geochemically speaking. And as to whether or not that is, I think you asked something about whether it was primitive life. Yeah, microbes, I think, are well accepted that those came before us. And so in that regard, we do think that they formed sort of the base of this ecosystem.
Well, the earliest life, it's really interesting.
It's all microbial.
Yeah, but that's sort of potentially, and I don't know if you've done enough study yet, but potentially pushes the oxygen meter back a little bit, perhaps before the oxygenation event when the cyanobacteria appeared. And here we have a source of oxygen deep in the ocean. Atmosphere wouldn't have had it, but deep in the ocean might have had a little bit that early, which means could there have been oxygen using microbe down there before Earth had its atmospheric oxygen, or is that a step too far?
Well, I think we might be entering the realm of speculation, but it's fun to think about. So let's think about it. Yeah, we know that complex animal life requires molecular oxygen. So that raises some interesting questions because we know that the oxygenation of Earth appears to have happened stepwise. I think that the fundamental steps behind the GOE are still valid. And it's really hard to sort of, how do I put this, provide a geologic context to support that argument, just because, as I understand it, the oldest polymetallic nodule deposits that we've found in the geologic record are only about 400 million years old. And so the GOE was about 2.8 billion years old. And again, this number gets pushed around as we increase the sort of the geologic characterization of the rocks at that time period. There's some really interesting isotope work that indicates that, the story isn't quite as simple as we had first thought. In regards to, and I want to be careful here, so, if our oldest deposits of these minerals are only 400 million years old, I would want to see a deposit of manganese nodules or perhaps a metamorphosed nodules before we can really start making that claim of 2.8 billion years ago.
So how would you recover such a thing? Would you just core down and hope you get a nodule deep from
so in that regard, we're looking more for uplifted geologic formations from that time period. And in that regard, we're a little bit limited because most of our deposits from that time period are either shallow ocean or terrestrial deposits. And so it's a little bit like, we're trying to, I guess there's some parallels with the exoplanet problem, where it's sort of really easy to find the big Jupiters, but we're kind of, maybe a little bit biased here, but we would really like to know more about those rocky planets. And so this is sort of a similar situation where the easiest things for us to measure might not actually be recording polymetallic nodule deposits or where they could form. And so, for example, those deposits that I mentioned that were about 400 million years old, those are in like France and Germany, and those would be associated with basically the ancient Mediterranean Sea, which I believe was called the Tethys Ocean. And yes, the Devonian, right? It's the age of the fishes, and that's another problem, is that a lot of our examples of uplifted oceanic crust are really not that old. And in part, that's because it's much denser, and so it tends to get subducted and recycled back into the lithosphere at a much higher rate than continental crust.
That is something that I think about perhaps a bit too much in thinking about exoplanets, is that Earth is really complicated.
Mm-hmm.
Like unbelievably complicated. And then, you talk to these scientists that have to weed through it, and it takes a long time just because there's just so much situational stuff going on. Well, I got news for the planetary scientists. All of the planets and exoplanets are like this.
Mm-hmm.
And you're just going to find, imagine finding a manganese nodule on the seafloor of Europa.
Wow.
Or something like that. And imagine the mystery,
No, that'd be a game changer for sure.
Well, it would also be an oxygenator, because if you've got this same process going on in an ice shell moon, that's a source of oxygen, which could expand out the possibilities of life in those subsurface oceans. What is your view on that?
Oh boy. So let's see. So most of we want to find a nodule first before we start doing these things. But it is generally accepted that the interiors of the planets are geologically active. So if you have a source of reduced metals and seawater that is similar to ours, it's in the realm of possibility, but we do start to border on speculation. Now, in terms of trying to get some of those deposits to see if they're there, that starts to become an engineering challenge, because not only do you need to get through that icy exterior shell and deposit, a lot of the designs I've seen to explore the oceans of Europa or Enceladus sort of involve things that look like sort of like either a flying saucer or like a wedge or even like a kite. And the idea is that you can deploy a swarm of them to cover a greater area. So it sort of deviates from that traditional sort of single rover model that we use for a lot of planetary explorations on like the moon or Mars or places like that. Now, that being said, if you're in the water column and the European Ocean is predicted to be even deeper than our own, you still have a long way to go before you'll get any of those samples. And so that would require sort of a change in design for these future mission concepts, where you would need to get to the deep sea, the seafloor, right? And so we have technology that can do that, there's deep sea landers and things of that nature. But as I understand it, a lot of the focus has been on a lot of the aquatic geochemistry, not necessarily mineral deposits. Yeah, that's a good question.
The other problem too is contamination. You don't want to contaminate Europa. So I think the focus rightfully on Europa and probably Enceladus is going to be the plumes.
Yes.
Look at the water spraying out of that moon instead of digging into it, which thankfully we can do a lot easier than sending a robot deep into the European Ocean.
Yeah.
Now
exactly
with
right.
Yeah. So I think the game plan now, by looking at the plumes, is the way to go. So this idea of all of these polymetallic nodules populating the Clarion-Clipperton Zone, and there are a lot of them. It's sort of astounding, the number. You look at that seafloor and all you see are these nodules. And if those are contributing to an ecosystem, and we don't have a full understanding of oceanic ecosystems, would it be dangerous to mess with it? In other words, there are a lot of plans, and have been for many, many years, to mine these because of the metals that are coming out of the volcanoes and get deposited here. Those are very important metals, that some of them are rare earth metals and all this sort of interesting profile. But don't we need to understand all this stuff before we large scale mine the ocean floor for these nodules?
Yeah, so the preliminary studies that have looked at the effects of deep sea mining indicate that, and I think some of these were first started in the 70s or 80s, and when they've gone back to look at them, by all visual accounts and with the measurement techniques that they deployed, it didn't really recover. There's a lot of literature to back that up. And so I think it is important to have a good understanding of not just the geochemical processes that are occurring down there, but also what ecosystem services those provide to us. And especially because this is such a fragile environment, right? There's almost no sedimentation. And so if you start altering that ecosystem, you could actually sort of snuff out some of those ecosystem services before we even know what's happening. And so I think in that regard, my goal as a scientist is to provide as much accurate and precise information to the UN's International Seabed Authority so that they can make the informed decisions. So seabed resources that are in international waters are sort of designated for the common heritage of mankind, at least in their charter. And so I think it is important that if these nodules are decided to be a critical part of our future in terms of resource extraction, then we should probably do it in a very careful way. And so I know it's a very sensitive issue. And yeah, my main goal as a scientist is just to provide relevant and accurate information to the people who have to make those hard decisions. And you're exactly right. The amount of metals that are there in just the Clarion-Clipperton Zone is actually greater than the known reserves on all of the terrestrial mines. So this isn't like a slice of the pie. This is a whole new pie with a completely different recipe. And that recipe makes these lumpy looking space potatoes that carpet the seafloor. So there is a lot that we need to understand about this process. And I think that the direction to take is probably to understand the system before we alter it, perhaps irreversibly.
Now, is the CCZ abyssal the only place you find those, or are these polymetallic nodules in other areas of the oceans?
Great question. So yeah, these nodule fields have been found in discrete regions of just about every ocean. So whether it's the Arctic or the Indian Ocean or the Pacific, there are nodule fields. The Clarion-Clipperton Zone is highly regarded just due to the high abundance of the nodules and also the large extent, the spatial extent of it. So right, this is certainly one of the biggest ones. And yeah, it does sort of raise the question, don't go after the biggest and most pristine one if you don't know exactly what's going to happen. You know, I could see that argument. But again, from a mining company's point of view, you know, that's the best one. So they're going to want to go for that one. So this is a very complex geopolitical situation. There's a lot of bordering claims and even overlapping claims. And I expect this is going to continue to be a point of contention amongst the nations that have claims there.
Everything in the ocean is, from fisheries to this, you know, there's a lot of argument, but yeah. I wonder if there could be a middle ground where it's treated something like forestry, where you're only taking part of it and leaving another part intact to where the zone can survive and recover. But these nodules seem like something that take a while to form. How long does it take to form, say, a 3-4 centimeter nodule?
Oh, wow. So yeah, again, a great point to make. They do form very slowly. We're talking millimeters at a fast rate, millimeters every 1,000 years, and millimeters every million years is sort of the figure that I usually hear. So yeah, in that regards, it's not. It's a little bit different from forestry, right? So you can have a pretty good-sized tree form in one human lifetime. It would take several human lifetimes to create reasonably sized nodules, and that's probably an understatement. So let's see. I think, and just building off of your earlier point with maybe is there a middle ground? I've seen some interesting designs on like using essentially a different type of collector vehicle that is using like AI to only grab nodules that don't have any animals connected to them. But yeah, you're right. There's likely like a density of the nodules, and if you go below that, you could lead to a collapse or something like that. Now, again, I don't know what that number is, but it does seem like in ecology and resource management, we've seen that before. And we've seen it before with resources that appeared limitless. So, for example, when American pioneers were crossing the interior of the U.S., the American bison appeared limitless. And it was harvested in great quantities and perhaps not treated the best. And, there's pictures from that time period of buffalo skulls essentially being piled into little mountains. And I would sincerely hope that we don't make that mistake again, where it appears that we have a limitless resource that we extract at high rates and maybe don't fully understand the ecosystem services that those provide. So, for example, the rich topsoil that all of our farmers depend on was undoubtedly influenced by those American bison and their ability to enrich the soil around them.
Well, I would imagine the hope is that we would get to a point where we have enough metals.
Yes.
Where we have enough in the recycling. We just got to be better at using our old metal. But once you have a metal, it doesn't go away.
It's true.
It's there forever unless you transmute it into something else in a reactor or whatever. But almost every atom of aluminum we've mined is still here with us.
Agreed.
And eventually you just end up with a lot of aluminum, and we could go back and mine our trash for a lot of these metals.
I think one day, we will realize the value of some of the things that we disposed of carelessly. But yeah, you raise a good point. I think the European Academies of Science, they have a council that estimated somewhere between 40 and roughly 3/4 of Europe's clean energy metal needs could be met by recycling alone as early as 2050. And so, right, that is a huge market, and that is, if you can do that, that likely reduces the demand for some of these precious metals. And so, yeah, I think being a little bit more efficient with how we do things, with recovering some of these waste products. But it's also important to note that battery technology has come a long way. So, I'll read summaries of articles where they're making stretchy batteries, carbon-based batteries, and things like that. And so it could be also that as our technology progresses, we'll need less of these metals as well.
Yeah, that happens where you're able to build things smaller, miniaturize them, and still get the same job done, but use less materials. There is, however, a rather hopeful aspect to this idea, and it comes from a quarter you wouldn't expect. Jewelry. Mm-hmm. Very, very little silver and gold gets thrown away. Mm-hmm. Compared to the amount that gets scrapped, so people end up with a bunch of broken chains and stuff like that, and they're like, that's gold, that's silver, and they go and they sell it to a jewelry store or buyer, whatever, and get some money out of it. That happens to a much smaller extent with aluminum, but if you had that sort of incentive where people adopted the same attitude towards, metals like whatever, that they do with gold and silver, then you could end up with a pretty efficient system, I would imagine, I hope. But it all depends on attitudes, of course.
Yeah, I think, and that's something, like you said, is kind of hopeful, is that there are a lot of solutions for the problems that, as a society, we all face now. And, at the risk of sounding radical, if you recalled every single penny and just harvested the copper off of that, I'm sure you could get pretty close to electrifying, America at that point. Now, that being said, I like pennies, so I wouldn't necessarily recommend that or anything. But it is, if we are able to think outside the box, I'm sure that there's solutions for a lot of these problems we face.
Oh, sure. We have a lot of metal. Yeah. Like I said, very few atoms of metal outside of a nuclear reaction have ever disappeared off this planet. So you could, and I think eventually you just get so much. So much. And with population growth slowing and things that are happening now, it's like, we may end up with plenty and not have to mine it, which would be nice because, you wouldn't have to mess with certain areas of the earth like this zone. Yeah. Now, the next subject is something that is particularly close to me because it really reminds me, it's one of those times where Earth becomes an alien planet. Snowball Earth, where this planet almost seemed to have frozen over almost completely. How's that play into here, to this with that? Because that's so different. Could these nodules have even formed? Again, is it conditional that these things only have started appearing 400 million years ago?
Okay, yeah, that's a great point. So let's see. We know that the nodules need very low sedimentation rates to form, because if you get too much sedimentation, because they grow so slowly, they'll basically get buried. So you need to have that growth rate faster than the sedimentation rate. And so glaciers and ice sheets can do a little bit of both. So, right, if you have a terrestrial-based glacier, that is one of the most powerful erosive forces on our planet. But at the same time, if you have like sea ice or things of that nature, you can have like glacial, I think they're called drop stones that can, we've seen in the fossil record. But I think the sedimentation rate generally goes down. In addition to that, the amount of photosynthetically available radiation is also going down because unless the ice is thin and you can have algae forming on the underside, most of that sunlight is going to be reflected back into the atmosphere and ultimately space. And so that is kind of an interesting point, right? So we have these snowball Earth events. We know that these have sort of acted as bottlenecks or evolutionary drivers, even potentially for the development of complex life like ourselves. In terms of active deposits, now, I think one of the places you would have to see this, it would be in the Arctic Ocean. And I know that there are deposits of nodules in the Arctic Ocean. So I think with that knowledge, I think we can say that the nodules can form at least under seasonal sea ice cover. We know that the Arctic does, lose a lot of its sea ice during the summer months, but that doesn't seem to stop the nodules from forming there. So that's a great question.
So they can happen in the cold environment of the Arctic. That's interesting. Under ice. How about Antarctica? Do you see anything under the shelves there?
Now this could be a literature gap for me. Now, I think in the Southern Ocean, unfortunately, I don't know the answer to that question. But given their abundance in every other, I guess, ocean, I would expect that if we haven't found them there yet, we may in the future.
Yeah, it'd be interesting because I don't, the Southern Ocean is the one we know the least about, as far as I can tell. And boy, that's another remote area. Now, what is it like doing an expedition like this? In other words, how long does it take you? Where do you leave from? Do you leave from one of the local volcanoes, Hawaii, or South America, or something like that? How do these expeditions unfold? Yeah, so they can unfold from a number of different places. So I know some of my colleagues have left from Hawaii, like you said. I think some of them have left from areas in Central and South America. Now, on this cruise, our port of call was San Diego. And so we basically just went due south from San Diego for, I believe it was 4 days. Not quite full steam ahead, but we were going along at a pretty good clip. So it really does take a long time to get out there. I think sort of the home port is going to be dependent on the organization that is funding. So in our case, the metals company was sending us out there. But if you were working for NOAA or HUI or something like that, you would likely have a different port that you would sort of be leaving from. In our case, so and I know other ships are different. I was working the night shift from midnight to noon. My boss, Jeff Marlowe, was working the day shift from noon to midnight. So it was, continuous operations 7 days a week for the duration we were out there. And we were out there for a little under 2 months. I think it was 4 or 5 weeks. So it was a long cruise. And I would say that, most good field experiences have action, drama, and adventure. Anytime you have that many passionate and intelligent people together, I think that tends to happen. So, it is like a little bit of a village out there, except you're on an island, and that island happens to be your ship. We were really lucky to have an awesome captain. I really enjoyed all of the crew that I was able to interact with, same with the scientists. And I think that makes a huge impact on not just the quality of the research, but also the quality of the time spent out there. Now, what are the next steps to further study this phenomenon of dark oxygen forming deep below the surface of the ocean?
Absolutely. So we really want to try to nail down these mechanisms. I think there's still a lot of work to be done there. We can measure it in more locations to see what the range of oxygen production is. And I think it's also important to try to understand that not just the small scale or what we can do with deep sea landers, but how is this actually impacting the ecosystem at large? So we know that some amount of oxygen is coming from Antarctic currents, right? You have downwelling currents, but those are at 200, 250 micromolars per liter, which is less than some of the rates that we were seeing. So it doesn't necessarily it doesn't really account for the measurements that we were seeing, and that water also has to travel thousands of kilometers before it gets to the Clarion-Clipperton zone. So you would expect some amount of microbial respiration to occur during that time period and reduce that starting oxygen content. So yeah, in terms of things that I'm focused on specifically, we're looking at some of the geomagnetic properties of the nodules, as well as the functional genes that are associated with the microbial community present in the nodules.
Now, my last question for you is this. Ammonia oxidizing archaea. Mm-hmm. Other possibilities for the production of dark oxygen. What else is on the table potentially?
Well, yeah, and just given how much of a shock this was for me in particular to come across something like this, just measured production, so there's electrolysis. I think that is a very promising option. There's the mineral decomposition. So you have things like manganese oxides. So again, there's a lot of oxygen that is attached to the manganese atom. You can have radiolysis. There's these intriguing little microbes there that I'm very interested in, regardless of whether or not they have a major component of the DOP. What else? I don't know. Those are sort of the ones that I can think of off the top of my head. But we do explore a number of different options in the paper itself. And so I would refer people to go back to that if they were curious about that.
All right, Peter, thank you for joining us today, and I wish you good luck in further work on this, because this is new. This is new territory of oxygen production that, I don't know, seems important to me somehow in an astrobiology context, but also scientifically. So I hope you'll check back in with us as your research continues.
Yeah, I really hope so too. And yeah, thank you for reaching out to me and setting this all up. And I've had a great time.